In this video we will initially derive Kepler's third law for circular orbits and then adapt it for large planets or binary stars. First, let's quickly recap Kepler's first two laws of planetary motion. Kepler's first law states that planets move in elliptical orbit with the Sun at one focus. Kepler's second law states that a line joining a planet and the Sun sweeps out equal areas in equal times. This means any planet orbiting a star must travel faster when closer to the star and slower as it moves further away. Now to derive Kepler's third law for circular orbits, at first we will simplify our model for planets by assuming that they move in circular orbits. We will start by considering the forces acting on our planet. We have the centripetal force that causes our planet to move in a circle. This force is provided by the gravitational attraction between the planet and the Sun, which we can express using Newton's law of gravitation. As these two forces are equal, we can set them equal to each other. Omega is the angular velocity, which we can define in terms of the orbital period t. We will then square and substitute this into our equation. Next, we can group our terms to isolate t squared on one side of the equation. Finally, we can rearrange to get Kepler's third law, which states that the square of the orbital period is proportional to the cube of the semimajor axis of the orbit. The previous derivation assumed circular orbits, which for the most part is a reasonable approximation for many planets, where their mass is very small compared to the star, so the center of mass of the system is within the star. However, for very large planets or binary star systems, the center of mass can lie outside of either body. This means that in our original derivation, the distance for gravitation and for centripetal force are no longer the same. Gravitation relies on the distance between the two objects, whereas centripetal force relies on the distance from each object to the center of mass. Let's first visualize this and define some terms. Here we have our large planet and its star. The distance between them is d, and the distance for each object from the center of mass is r1 for the star and r2 for the planet. As these two objects orbit their common center of mass, they are in equilibrium, so there is no net moment and no net force on the system. This means that the moment both objects create on the center of mass must be equal. From this we can derive that m1r1 equals m2r2, and from this we can also derive that r1 plus r2 equals d. From this we can substitute r1 and r2 in terms of d, giving us r1 equals m2, m1 plus m2, d, and r2 equals m1, m1 plus m2, d. Now we can adapt our derivation of Kepler's third law to account for this. Now we have our formula relating the distance between the objects, required for gravitation, and the distance from the center of rotation, required for centripetal force. We can add these to our formulas and rederive Kepler's third law. So now our formula for centripetal acceleration becomes m1 omega squared r1 and our law of gravitation becomes gm1 m2 over d squared. First, let's remove r1 from the equation by substituting our previous equation for r1. Next, equate these two equations to each other as we have an m1 square meter term on both sides. These cancel, we substitute our definition for omega squared in again, and finally we rearrange to get t squared as the subject. For a system where m1 is very much larger than m2, then m1 plus m2 approximately equals m1. So this simplifies back to this version of Kepler's law back to our previous version. In summary, Kepler's three laws are as follows. 1. Planets orbit their parent star in ellipses with the star at one of the foci of the ellipse. 2. A line between the planet and the parent star will sweep our equal areas in equal time. 3. The square of the time period is proportional to the mean orbital radius cubed. We have shown that in this video the third law also holds for binary stars where the center of orbit is not within the larger body. Hopefully this video has helped, and if you have any questions post them below, like and subscribe.